Hi, my name is Greg Smith, and today we are looking at the iBook G3 Clamshell Touchpad. So today we're going to look at repurposing the iBook G3 Clamshell Touchpad. The project is to completely repurpose the iBook and make it modern using a Mac M1 processor. And so we wanted to use as many of the original parts as possible, including the touchpad. So we'll go through the process of tearing down the keyboard unit that has the touchpad in it, and then removing the touchpad and interfacing to it with a Teensy and then a Raspberry Pi, and the software that goes into making it work. And then we'll find out whether or not we can actually use this touchpad in this project. Okay, so once you have the unit taken apart, you've taken out the, this is the bottom half of the keyboard, so the keyboard normally fits in here. And what we're going to do is we're going to take this metal piece off to expose the touchpad. I've actually taken this apart already. This is a recreation of the work that I did when I originally took it apart. Okay, so you can see here that the flexible cable or flexible PCB is coming out of this slot. Under here is the trackpad. Over here is the power switch, which you must be careful with. There's a spring in here and that'll pop right out. And then over here is the speaker. And all along here are these sort of like plastic rivets. And you have to be very careful when removing these because they will bend the metal case. So if you would have any intention of putting this thing back together once you've taken it apart, you would need to be very careful when you take these bits off. So the first thing I did was to disassemble this this power button. It has sort of a latch up here at the top, and I'll see if I can zoom in on that. So up here, there's a little hook where it like latches in to the rest of the keyboard base. And then this is held down by a combination of glue and again, these are sort of like plastic rivets. And I had to apply some heat to kind of loosen it up a bit and then pry it off. And when I did, you can see here, there's a spring, and then this cap, and then the button itself comes right out. And then over here, I had to apply quite a bit of heat to the speaker, as it was also held down with glue and rivets. And when it comes out, the speaker is nestled in here with a little rubber grommet, and that comes out like that. And there you have that bit here. Now the rest of this, these little notch here, these little holes notch into the actual base of the chassis, and you have to be very careful when taking these off. I applied heat to each of these, and you must be careful when applying heat that you don't apply too much because it will warp the plastic chassis. And then this comes off. If you're gentle with it, it will pop out one bit at a time, and it will come out as one big piece. So the other thing that you notice here is that the backside of this is almost white. So while you can see here, this is kind of chrome and shiny. This is kind of white and flat colored, and that makes the translucent part of this case look kind of white when it's covered up. So it's actually very nice. So you want to be careful with this. Now this other bit here, you can see this little, and also this piece of tape or plastic that covers up. First off, this is the trackpad, and this is a ground connection, so that when this sits on top, it creates a ground, and then this constitutes a bit of a Faraday cage that prevents the electrical noise from getting out into the world, and it's part of the FCC requirement. So here is the touchpad. Again, this bit of the touchpad is held down with like these little plastic rivets. On the other side, you can see that this is where the button, the touchpad or trackpad button is housed, and it will flex down. And then this bit up here is a bit of non-conductive plastic that is used to cover the trackpad, but it is held down with adhesive. And again, I applied some heat to loosen up the adhesive. And you can see here, this is what the trackpad looks like. And these are little capacitive pads that, as your finger moves over this plastic area here, it creates an inductive, I guess, resonance, and that's how it tracks your finger across the pad. Now this is all held down with adhesive, so I had to apply a little bit of heat here in order to pull it up. Again, you have to get these little plastic rivets to loosen up, and then once you do this, it just slides right out like this, and that's the entire touch button assembly. Okay, so this is a Synaptics touchpad. Synaptics makes these things kind of for all different types of computers, and they come in different flavors. Now this again was held in with adhesive, so you have to be careful when taking it out. There you go. And that it completes the disassembly of the keyboard chassis. This is a Synaptics touchpad. Synaptics makes all manner of human interface devices. The number that you see here, TM41P, indicates that it's a touchpad, and M for mouse emulation. The 41 tells us that it's the T1004 microcontroller, and the P tells us that it's one of three types of mouse emulator. P, it's a PS2 emulation, and if it's a S, it's serial emulation. If it's finally a, it's Apple Desktop Bus, or ADB emulation. And this caused me to go down quite the rabbit hole, because this says that it's a P. I went to a lot of trouble to first try and emulate the PS2 mouse. So if you look here, here's another picture that I found on the internet where it describes the different pins coming off the processor and where they go into the flexible PC cable. There's a data line and a clock line, and in PS2 emulation, the clock line strobes at a particular rate, and then the data line either sends data to the host, being the laptop, where the finger is on the touchpad, or you can send commands down that same line, instructing the touchpad to do different things like reset or set its resolution and things like that. So I spent a lot of time trying to figure out how to emulate a PS2 mouse. I connected this to the Teensy, and I sent PS2 Protocol down. I actually connected this to a terminal that was expecting a PS2 mouse input. That didn't work. So after quite a bit of study, I finally concluded that this was in fact not a PS2 emulation touchpad. I was Googling around, and I came across this picture on this very cool website that showed a picture of a touchpad, and it had the numbers TM41T. So that threw me for a loop, because I hadn't seen that identifier before. So I did a little more digging in the Synaptics PDF documentation, and found that T stood for TTL serial emulation. So this meant that it acted like an RS-232 mouse with TTL levels, meaning between 0 and 5 volts. And this was kind of a breakthrough. Once I figured that out, then I could actually start interfacing with it, and that took me down a path that ultimately led to being able to use it. So I spent a good amount of time trying to decipher the wiring on this device, and trying to figure out which pins were doing what. And I had some notes from sources I found on the internet, and then ultimately it turned out that like this pin 2, I think, is the left mouse button. Then this one pin coming out here from pin 4 is the clock, and then pin 5 was the data. That's how it would work if it was a PS2, but it's not a PS2. And so I spent literally days trying to figure out the PS2 protocols, and it did not work. Ultimately, what I ended up with was the mouse trackpad connected to a little breakout board, and then into the Raspberry Pi Pico. Got power and ground, and then this is the transmit. I take that back. This is the receive, and this is the transmit. And so I was able to read data from the trackpad, but I was not able to send any commands, and I still haven't been able to figure that out. But once I set the baud rate to 9600, I was starting to get some data, and so hopefully I can show you that as well. What's happened now is that I started to fool around with it. I set to 9600 baud, and I started to notice the data had a pattern, in that it would be like hex 8 something followed by 4 values, and so the data was coming in bursts of 5 bytes. So what I saw here, like you can see here, there's 8, 0 followed by zeros. So I assume then that 8 is the beginning of a frame, and then this number over here was either 0 or 4. That was a bit for finger down or finger up, 4 being finger down and 0 being finger up. Then these were the deltas, how far since the last motion. And if you look at this previous value up here, this 0, 0 goes with this 0, 0, so there's no motion in the X direction. And the two 7Fs are a -1. So that meant that I could sign extend these values and get numbers that were actually deltas in the X or Y direction. Now that the mouse is under control, I can move it left, right, up, down. I can also like tap it, and it will set the mouse position. I can tap and hold, and it will grab as if I had done a mouse press. There are also the capabilities to like do a mouse wheel, so I can just like push down and hold. I can scroll with the touchpad. Now I can't do like 2 finger gestures. I can do double taps, pretty much everything that you would expect to be able to do with an ordinary mouse. So now let's take a look at the code that I wrote to control the board. I used CircuitPython mainly because it allowed me to turn the Raspberry Pi Pico into a mouse by way of the USB port. So that's why you'll see a bunch of these imports for USB HID, for example, which is human interface device, and then the Adafruit HID mouse, which allows me to send mouse protocol down the USB port. Let's see, we also got time to manage the time between data frames, UART to be able to read data from the mouse as if it was on an RS-232 port, and so on. So the data rate I set to 9600. So the mouse wheel DY, I'm inverting the direction of the mouse because of the scrolling capability. This is the number of milliseconds between clicks that allow the tap on the touchpad to represent a mouse click. How long between pressing down on the mouse, and we assume this is a long press, which is used for emulating the mouse wheel, and then the mouse click press, which is how long we wait if we have between a click and then a press down in order to grab something that's on the screen, like a slide bar. And then these values are all values that represent the time at which something happened. For example, that a mouse clicked, or the mouse was down, that we did a mouse wheel, that we're dragging our finger, or that we were moving across the touchpad. And then the dx and dy are the distance that the mouse has moved since the last sample. Mouse init just does a initialization of the mouse. Sleep MS is a convenience function that allows me to sleep for a certain number of milliseconds. It turns out that the CircuitPython does its sleeping in fractional seconds, and then other like MicroPython used an integer milliseconds. So this just allows me to switch back and forth between the two languages if I need to. It takes milliseconds. We'll get the number of milliseconds since the device started up. Log is an alternative to using the print command. I can easily comment out print, and by using log I can easily remove all my printfs so that I don't have to see them on the console. UART init will initialize the UART device, and in this case we're using GP4 and GP5, setting the baud rate to whatever we pass in. 8 bits, no parity, and 1 stop bit with a timeout of 0, which means that it will not wait around for data to come in. If there is no data, it will, when we do a read, it will go into the next command. And here's the read command. If we set n, which is the number of milliseconds to wait, to 0, it will not block, and that's what this says here. So we do a read of 1. And then down here, if we want it to block, it will read and wait 1 millisecond. And if it still has no data, it will continue in that loop until data is available. And then finally, we could get back from the UART an array of bytes. So if it's none, then we just return none. Otherwise, we want to return the first value in the byte array. And then finally, we log that value out if it's not none, and then return the result. Sign extend, this is a very simple method for detecting if the most significant bit is set. Now in this case, our values are only 7 bits wide as part of the protocol, and so we check the most significant bit, which would be hex 40, and if it is turned on, then we subtract 80 from that, and that will give us a negative value, and otherwise it returns the actual value. Okay, so here's the main code. We do a UART init, setting up the UART, and doing a mouse init, set the mouse, and then wait forever. We will loop forever looking for mouse clicks. We get the current time, and then check to see if the mouse was previously set down, and if we're not dragging. And if we are, then what we do is check to see if the time at which we last pressed on the touchpad, had a mouse down, is greater than the amount of time it takes for a long press. And if that is the case, then we set the mouse wheel, because that's what happens when we hold down for more than 300 milliseconds. We want to treat it like a mouse wheel. We set that to the current time, and we turn off mouse down. We are no longer looking to see if someone clicked on the mouse. And now we are going into mouse wheel mode. The next step is to actually get a byte from the stream. If there is no byte, then we continue. But if there is a byte, then and it's greater than 127, which means it's a mouse click, we've pressed down, it's a hex 80 or hex 84, then we want to determine if it is a hex 84. If bit 04 is set, then we know that the user has clicked down on the mouse. We get the next 4 values, which are our Y1 and X1 values for determining the deltas, and then we sign extend X0 and Y0. In my experimentation, I never saw any values greater than negative 1 or 2 or positive 1 or 2, and so we do not need the first 2 set of values. We can just use the least significant bytes. So those are now our deltas, and if we now detect that the user had pressed down on the touchpad, then we once again get the current time, and now we start looking at the deltas. Have we moved in the X or Y direction? And if we are not moving in the X or Y direction, that means that this is a mouse click. And so we determine if we've already done a mouse click, and if we haven't, then we get the delta and check to see if it's been a reasonable period since the last time we did a mouse click. If it is, then we assume that what we're doing now is a click on the left mouse button, and we're sending a mouse press back up the USB to the host, which in this case would be a computer or laptop. We turn off all the other timers, indicating that when we are not checking for click, wheel, or mouse down, and we are now setting mouse drag to the current time. So what this is now going to do is allow us to detect if the user is dragging their finger across the mouse. Now, if this is not a mouse click, if you're not in a mouse click mode, but I was using mouse DX and DY as multipliers, so that the mouse would move faster and faster the more you further you dragged away from the origin of the mouse down. So that's why we capture mouse down. Now, if this was not a dx equals 0 and dy equals 0, which means that someone had touched on the touchpad, not just tapped it, but is now moving across the face of the touchpad, then dx and dy would have some other value than 0. So if we are in mouse wheel mode, then we will move the mouse in the dy direction and set the wheel value at the same time. So if we're not in mouse wheel mode, so in this case we are not doing a mouse wheel event, we are doing a mouse move event, and so we will move the dx and dy deltas. Now this dx value, the mouse dx value, is a multiplier, and the idea behind this was that as the user moved further and further from their origin, if they moved quickly, we wanted the mouse to move further, and if they were moving slowly, we wanted to find green motion. And so the first time they pressed down on the touchpad, we set dx and dy to 1, and then as we move further and further across the trackpad, we would multiply this value to kind of give an acceleration of the motion. So down here, again, we are taking the mouse move. If we are in mouse move mode as opposed to mouse wheel mode, we now calculate a new delta, which is the current time minus the last time that we moved. We set the multiplier to 1. And this piece of code here I commented out, but the idea here is that it's checking to see how fast the user is moving across the touchpad. I was able to use the settings in Mac OS to do this for me, but if you don't have those settings on your computer, you can use this piece of code. So the big idea here is that if you are not moving your finger very fast, that is, you're getting a lot of samples between mouse clicks or mouse moves, then you want to move the mouse very fast. But if you're moving your finger slowly across the touchpad, you want to move the mouse slower, and so you have a smaller multiplier. And again, macOS does this for us, so I was able to comment this out. Now finally, if we were in this mode of moving the mouse, we reset the last time that the mouse was moved to the current time, and we also remind us that this is not a mouse down event, that we are now in the mouse motion mode. At the top, if we are not in mouse down mode before, then when we see a mouse down event, we set mouse down to now. That happens here. And then down here, when we see a mouse up event, then we say, oh, we were previously in a mouse down, but it wasn't a very long time that it was mouse down. And if it had been a very long time, then for example, a short tap, then we would send a mouse click. But if it was a long press and then a release, we send a mouse release. So it's a very subtle difference between a mouse click and mouse release, but it's a very important difference when you're exercising the code. So all of this to say, it's actually fairly simple code that manipulates the mouse, that you can do a lot of these mouse capabilities, including not just tracking the finger across the touchpad like it was a mouse, but in the X and Y directions. You can also emulate a click, a hold, which would be a tap and then a hold or press down on the mouse for something like a scroll bar to scroll it up and down. You can do a press and then a drag, which is what you would do if you were, say, selecting text like this. As I mentioned earlier, there's no facility for capturing if you have two fingers on the mouse at the same time. And so this particular mouse pad is not going to be useful for our iBookintosh project. So this concludes the teardown and emulation of the iBook G3 Clamshell Touchpad. It turns out that this touchpad just isn't powerful enough to control an M1 MacBook Air, which is what we're going to be repurposing the clamshell with. So I have to find another touchpad to use. I have one in the shop, and we'll be looking at that next time. So please, as usual, don't subscribe to this channel, don't look at my other channels. Your time is precious. You don't have that much of it. Please don't waste it on anything that I'm doing. And I'll see you next time.